Cool. Um, in case you haven't find your partner on the project, I don't know how, just try to find it. You can use the Google chat. I see some folks discussing it, so definitely find someone and think about what you want to do. And you have to pitch on Wednesdays. So and for like 10 minutes sort of like short presentation, but basically talk about what you want to work on and talk a little bit about methodology, but pretty much just tell us what you're thinking and what you plan and sort of like set your own milestones, how you're gonna make it by the end of the semester. I should change this. Cool. Um, we could leave like 10 minutes at the end so that you can figure it out. Cool. Cool. Once again, the group project could be, building a new tool or, exploring using existing tools. But you have to try to do something new or novel. Any questions on the topics? Have you think about it? I assume so. Cool. Yeah, like 10 minutes. So, talk about what you want to work on, basically. Cool. Um, I'll see you on Wednesday on this. Cool. There's no question, then let's just move on. Just a quick recap what we've been talking about. So we are sort of like off bit on the slides, but anyway, we've been talking about AI song contest, and you've done the homework on that, and we are basically talking about these four paradigms of music generation, text-based, image-based, symbolic music generation, but also audio domain music generation, which will follow. And at the end, we will talk about this very confusing latent space systems, but those are now the state of the art, and most of the system you see nowadays, those famous one are based on latent space ones. So we have to take a look into it. And so in the last two class, we were basically talking about symbolic music generation. We talk about how you can generate these kind of, text-based music representation using sort of like RNNs, LSTMs, transformers, different models. But we were also looking into how you can generate music in this image-based representation, basically the piano roll that you see in any dolls when you drag some MIDI into it, or you are using your keyboard to do the synthesize. Cool. So for language model, approach is basically just doing this predicting next word game. So you're just basically looking into what's the chance that you get the next word, and you try to figure out what are those higher, more probable words versus less probable words, and that translate into some mathematical function. But that's basically the conditional probability. What's the probability of each different word given all the past words? So what you want to do with this machine learning or deep learning model is try to learn this, that some of the words is more likely to follow these given sentence, but some of the words are less likely. So with this, you can just do something like this. You can generate the sentence, even though in practice it's much more complicated. But that's basically the idea. Once you know what's more probable, what's less probable, you can figure out how you can sample from that distribution, or picking the most likely one, or maybe one of the top three most likely one, top 10 most likely one, and figure it out. Some randomness, but you can basically do generation with that. So we've been talking about how you can design, machine readable music language. There's a bunch. So we start from, ABC notation, which is very limited in its original form, even though later nowadays there are also people extending the ABC notation to make it more powerful to handle polyphonic music. But in its original form, it's just, monophonic music. So you can look at this, basically just getting the letter to represent the music in a fixed grid. So you can pretty much just generate something with that, just character by character or letter by letter generation. And we talk about, LCM, we talk about different model, but you can also use a much more complex representation, like a MIDI-like representation, doing like node on, node off, and time shift, so that you can generate polyphonic music. And we look at, again, using the same LCM, but now doing these, MIDI events generation. And but we can also do it with a much fancier music transformer. So I think the biggest thing we talked about last week is about music transformer, which is one of the most important neural network nowadays. So ChatGPT, lots of the Gen AI stuff are actually based on transformer models. So we didn't go into detail, but I think one of the key things you should know about transformer is the self-attention mechanism. Transformer itself is a very huge model, but this is the core idea of how transformer work. But basically what transformer want to do is something called self-attention, is that, when we are doing this, next word prediction game, we don't want it to be just uniformly just looking into all the past words. There are some words that's more important, and there are words that's less important. So we want to sort of like dynamically figure out which one is more important to determine the current, word generation. So, transformer, the key idea is just to learn this from big data, learns to how to attend to, everything you've generated so far, or, the input so far, and then figured out what's more important than the other. So this can be applied to music. When you are generating music, it will look at different part of the previous generation, and you will see that it's sort of like always looking into the first chord. And it is sometimes also looking into the current chords, because those are important information, so that what are you going to generate. But it also looking into if you are in somewhere within the some fast group of cluster of nodes, then you will look at similar pattern to determine what note you should do. And we look at this. Cool. We should just look at it again. This is pretty cool. Any question on this? The transformer thing? why we should do it. There's no particular reason, just that it's the best so far. And maybe we will see something new in the future. But this is currently, the best we have. And, it's like 10 years ago, people are looking into LSTMs, other models, but now people are, mostly using transformer. And there are also some new models like, state-based models, people are also using diffusion models to generate text, but you never know. Maybe 5 years later, no one is talking about transformer anymore. But this is sort of the state of the art, and most of the Gen AI service are using this kind of models. That's why it is relevant. And finally, we talk about, how you can make it into, multi-instrument. So this is just piano, but you can, figure out a way sort of like have the instrument in part of your representation. Then you can generate music with different instruments. There are different versions of it. Again, here you can append the instrument within that um, um, representation. Cool. And I think lastly, we try our best to talk a little bit about generative adversarial networks. But I would just quickly go through what we've went through. Let's keep this. So the key idea of GN, generative adversarial networks, is to figure out a loss function for distribution. So the idea is that what we want to do is this, given a bunch of random stuff, we want to map it into something reasonable. So think about, these could be noisy image, but we want to turn it into, a cat image or a dog image, or, it's just random white noise, or pink noise or brown noise, but you want to turn it into something, meaningful, say, I don't know, dog barking sound, music, violin sounds, or whatever sounds, but you want to turn something random into something, within, meaningful. So that's the idea. So that's how generative models nowadays usually work. So this kind of model, we call it deep latent variable models. But anyway, that basically means that we are going from some random distribution to the data distribution. And, since this mapping is very hard to learn, going from a totally noisy white noise to, a dog barking sound or a violin sound is just, you never know how to do it. So we want to use, neural network to do it. But the question is that, when you started, have a neural network, what you would generate is something totally different from what you have in your data set. So the idea is that how can we sort of provide some feedback for this neural network to learn better, to capture, if this is a bunch of violin sounds, how can we, if the model is generate some dog barking sound, how can we turn those dog barking sound and have the model turn into it, in a way that it generate more instrument-like sounds. So the idea is that, once you generate something and you have all your, ground truth data, how do you measure the difference between them? So there's no clear way to do the measurement. If you do just L2 loss, as we talk about, just take the waveform of one and take the other waveform of that and then minus them, subtract one from the other, measure the difference. It doesn't work because, here we were talking about, this what we call, generative model. So there's just no ground truth for what you want to generate. So anyway, here, the core idea of generative model, generative adversarial network is try to figure out a loss function by using another neural network. So this is what it works. Anyway, you have a bunch of images, a bunch of audio samples, but basically a bunch of real stuff. And then you have another generator. That's what you are interested in learning. So it goes from, some random noise, but it turned it into a bunch of, fake images or fake sounds. And what you have now is another neural network called discriminator that just going to, classify each of these samples. So the model, the discriminator doesn't know which one is coming from which, stream, but basically they are mixed together, and the discriminator want to classify each of them into real or fake. So when you're doing this game, the discriminator aims to, tell the fake samples from the real samples. But at the same time, this generator wants to sort of like fool the discriminator into believing these fake samples are real. So by playing this, like, the game, competition between them, you can sort of like do something cool. Cool. Let's jump to this. So anyway, so this is one of the models that you can use, GN to generate Pianoroll. So when you start, everything is sort of like pure noise. And as time goes by, as the training goes, so you will see that, the generator become better. Because, discriminator is so easy to classify whether this is fake or real, because this just looks so fake, and this one is still really fake. But, over the time, generator will improve, but also discriminator will improve because, later in the stage for the discriminator, it has to, rather than looking into, how many, just sum it up, this is way too many, notes. But, later in the stage, you will have to look at, not just looking into how many notes, but rather does it has, these horizontal pattern? Does it has a reasonable, drum patterns? Does it have a reasonable scale course rather than just random nodes? So, the generator improves over time, and so does the discriminator. Cool. Oh, good. You basically see what we want to do, but basically what we want to do is just apply GN to do Pianoroll, just like this. So just a little bit about Pianoroll. So Pianoroll representation coming from this, the old school player piano, how you can play Pianoroll, how you can play music from this kind of Pianoroll. So Pianoroll is basically, a bunch of like punch holes so that you can control this machine that it will control the player piano. Very hard to explain. We should just look at this YouTube video. These are the piano rolls. And there are, control system in that so that it can read the holes in the piano roll. So you'll see some holes that will be read by this thing. jump. I want to show you that again. You can reset it, which is pretty cool. Cool. So, that's the actual piano roll that we were talking about. And, there's a bunch in all different music libraries. But basically those are sort of like, think about it like control, like the early computer that you use those to control a player piano. And in fact, this is also a player piano, but it's not controlled by Pianoroll. But nowadays we are using MIDI to do the same idea, where and when and how long to play each single note. That's what player piano is going to do. Oops. Cool. So basically, piano representation, turn the thing that you just saw. It's, sort of like vertical, but, now you turn it 90-degree. Now, you turn it left or counterclockwise. For 90-degree, then you will get something like this. So, we look at these piano roll usually in this shape. So at the horizontal, x-axis, you have the time. And at the y-axis, you have the pitch. So, basically, if you zoom into it, you will see, different notes at the same time. There are, lower keys, but higher key at the same time. Each single time step, we coded the minimum note length. So you have to quantize it in any sense, this digital world. And usually we will have, brightness represent the MIDI velocity, but sometimes, it will be binary piano roll, then there's no sense of velocity. And it depends on how you do the piano roll. Sometimes it could be expresses timing. So that basically means that your sort of like tempo can vary, and there could be rubato rather than, just flat timing, the same tempo constant. And if you're doing without, expressive timing, then it becomes this like sort of like grid that, there's like repeatedness inside the piano roll. So the core idea of, doing piano roll for music is on the idea of these, reusable pattern detectors. So, remember, as you may recall, when we were talking about, convolutional neural network, we were talking about, how can we learn these different detectors? And we sort of like explore how they can be done in that, what's that? Musical note classification on ANSYS. So, it's basically just learning these reusable patterns and, try to apply it in, different things so that you can detect all these different patterns. So, why should we use piano rolls in any sense? So, the core idea why people are interested in using piano roll is that you definitely see these patterns, again and again. So it's sort of similar to what we want to use in CNS that, there are patterns that's, translational invariant, which means that you can use the same patterns and sort of like do, like a convolution, basically just slice through it and you can detect all the different patterns. And you can see that, sometimes it's just moving in the temporal axis, just moving at different time, but sometimes you can, think about a major chord. If you just move the pitch, above, it's still the same, degree between the notes within major chord. And, same for minor chords. So same for different chords. So, there's a sense that you can learn something about these, reusable patterns from piano roll. So the reason why we're using it is like melodies, arpeggios or chords, scales, are all translational invariant in some sense in the temporal and pitch axis. Cool. So, that's why we were interested in, music generation using GNs. Cool. So we could just look into some of the example. So this is sort of like one of the earliest attempt to use GN to generate something. So this is called MIDI-NET. We won't go into detail. But how MIDI-NET work is that, it's just looking into single measure, single bar, simple melody line. That's it. So, it go from some noise and then you use this generator to turn it into, larger, higher resolution. And at some point it will just expand into that, piano roll format at some point. And for the discriminator, is just looking at this example versus, the real, fake generated one and real generated one, and try to do this, binary true, false, true, real, fake classification. So, this is a measure. I do have these animation. And something different for MIDI-NET is that it actually are not doing just pure generation. It's actually conditioned on the previous measure. So think about it this as a very simple way to generate music. That is, you only have access to the past measure without all the other things. So it's a very, very lossy compression or assumption that the current measure, current bar, can only access to the previous bar and not the others. But anyway, if that's the assumption, what we can do, this is the earlier attempt, using GN. But anyway, if you have the previous measure, then you can sort of like use it also as the condition to the discriminator. So the idea here is that, now the discriminator is no longer just looking at just the current measure, but it also looking at the previous measure to see whether this is a reasonable continuation for that previous measure. So that's sort of the idea, how you do, conditional generation in a GN model. And you can also add, chord progression as the condition to it. And the same idea apply. You just put that into the discriminator. So that discriminator now is not just looking at whether this measure is real or not, but rather looking at this measure, but also the chord progression. Does that do that match, basically? So these are some of the generated samples. So it's just generating the melodies. The chord progression are given. Always interesting to listen to these samples, given nowadays we have so much more powerful models. But anyway, this is the early days. So, you can also see that progression. So here, piano roll is unfortunately, again, turn back to its original form. So, time from top to bottom, but, notes from left to right. So this is the original piano roll that you see in that YouTube video. So when you train for 5 epochs, so each epoch meaning that you go through the whole training data once. So 5 epochs meaning that you go through your training data 5 times already. So you can see that is sort of like converge into certain notes, and for this case, certain pitch in that chords likely. So over the time, it will become more, more, I don't know, variation, but also be more confident in some sense in that, you should just pick one note at a time because we are doing monophonic melody. And these are the ground truths. So you can see that, there are definitely, certain note that's more likely than the other rather than, just randomly picking a note. Cool. So the other example is VScan. So now we just extend the same idea, but now we just do more, instruments. So these are drums, piano, bass, guitar, and synth. Basically, synths cover any other instrument. So now these piano roll is now become a much complex matrix. It's actually a tensor, but basically you have that 5 piano roll at the same time. So you not only have just piano, but also other instrument. So this is the drum instrument that you can see that it's just like single shot patterns to trigger it. But anyway, this is the thing that we just saw, that you can generate this over time from noisy stuff and later converge into these beautiful piano rolls. Anyway, we won't go into details. This is the whole system diagram. I made it, so I regret it. It just looked terrible. But anyway, that's what it is on the paper. So the core idea is that we have some bar generator that just doing each measure generation, and then you have another generator that turn it into 4 bar rather than just one single bar. So you use that bar generator 4 times to generate 4 bar phrases. So in this where we just do at 4 measure generation. That's still the early day of GN. And for GN, it's not like transformer. You can generate things just follow auto regressively, that you can just continuously generating stuff. But GN is more like generate a fixed amount of data or fixed length of data, rather than unlimited generation, sequential generation. But anyway, once you have these 4 measure of piano roll, what you want to do is to you have another discriminator to look at these are the real piano rolls, and these are the fake piano rolls, and whether they are the same. Anyway, with this complicated models, what you can do is something that we just saw. Over time, the piano roll will just improve. The piano roll that you generated, you will improve. But at the same time, the discriminator will improve as well. So this is some of the examples. Oops. It's just 4 measure of music at one time. Well, I think we're good enough. So 7 years ago, that's what we have, and think about what we have nowadays, and maybe that's it. So you could imagine how things will evolve. But these are much easier because it's MIDI sort of like symbolic generation. So I turn it into synthesize it into the audio using existing, just connect to a DAW basically. There's a question on chat. What do you use as training data to train the bar generator? Oh, I forgot to talk about this, but this is trained on a data set called lock MIDI data set. So basically 200,000 of MIDI. So think about MIDI is it's an old protocol. So it's usually music 30 years at least, or 50 years ago. But music in the 70s, 50s ish, maybe not 50, 70 to 90s mostly. So they have a bunch of MIDI files for those. Nowadays, people don't really use a lot of MIDI files nowadays, but that's sort of the characteristic of that sound. In this case, you don't really get a sense whether it's 70 or 90. It sounds like, I don't know, some other genre. But if you train it on lock MIDI, what you're expecting is those 70s-ish sounds. Cool. So something like, I don't know, Jackson 5 era. Cool. Any questions on GANs? So even though you will likely, heard this word anymore nowadays. Most people are talking about diffusion, transformer, but again, these things that we talk about in this class, all the things that we talk about in this class is still being applied nowadays. Just that the naming just pick the most fancy words. So latent diffusion model has everything in it. It has transformer, it has CNN, it has scan, it has VAE. It sort of have everything that that's being covered in this class. So we select some of the representative models to talk about, and the reason why we are talking about it is that because they are still used today. So it's not like these models are just one era over the other and the old stuff will no longer be in use, but rather they just turn it into a different way within your model. So is the discriminator and the bot generator getting trained in parallel? So the idea of generative adversarial network is that you take turn training the generator and discriminator. So you train the generator, so generator become better, and then you train the discriminator also become better, and you just take turns, and so they will improve over time. So think about it more like a Tom and Jerry way. So you have generator improving, but Tom also improve over time how you catch. Anyway, so that's the idea. You train them simultaneously, but also sort of like take turn in practice. Cool. So I guess we could look into another very complex model. So bear with me on all these models. There's a lot of details on how these models work, but the idea is not to, it's not to get lost in these models, but rather get a sense how these model works under the hood, scrapping some of the surface, at least get a little bit more deeper into how these model works so that you can, get some sense when you are using these tools, what they are actually doing. So distribution model is likely something you also hear a lot nowadays in news or whatever things. So diffusion model is sort of like the state of the art in generating images, but also audio. So Suno, or think about other music generation system. They are mostly using diffusion models, but also think about image generation system. So Adobe Firefly, DALL-E, OpenAI DALL-E, and Google Image Gen. They sort of most of them are using diffusion models. Some of them are not, but half of them I would say are using diffusion models. Cool. So what is diffusion models? So we should start with this thing. So this thing is called autoencoder. So it's something look like this. It has the input and output the same. So these are some neural network. But anyway, the idea is that you go from 6 neurons, and then you turn it into, you sort of like compress it, but now you decode it again back to the original shape. So you can think about it, it could be, an image, say 32 by 32 image, and then you turn it into something, more compact, and then you turn it back to 32 by 32 image. But anyway, the idea is that the input and output would be the same. And you can train such a model by reconstruction loss. So basically just, measure the difference and try to train this model so that it compress the information into the bottleneck. You want to turn 6 pixels or 6 neurons of information into just 4 and then turn it back. So you can think about it as sort of like a codec. So, if you train such a model, you can get something like this, that, you have original, some images, and then you can turn it into a much compact form. So think about it like, like a JPEG compression, or, whatever compression, but in a much more higher compression rate. So what you will get from these is that, think about this image, you have Lee, but the reconstruction, there's no logo that Lee, because, those are very detailed information that happened only once in your data set, perhaps. But, the general shape will be clear in most cases. So now what we want to do in diffusion models is to have the same idea, but now we want to do this called denoising autoencoder. So the idea is that, can we sort of like put into some noise into this image, but still can we ask the model to generate the clean one? So this has been shown to be possible, that the model has the ability to get rid of all the noise, but somehow figured out what the core image is. So this is called denoising autoencoder. So it's sort of like a codec, or an autoencoder or neural codec that is noise robust, that it will just get rid of all the noise naturally. So this is the idea how we can build diffusion model. So again, what we want to do as a generative model is, rather than just generate a bunch of stuff randomly, but, what we want to do is, going from some random distribution. So, in the case of like, MuScan, is that, you have some noisy input and you want to turn it into some, real piano rolls. So basically what you want to do is doing this mapping. So once again, all neural network are just a mapping that you are trying to learn to map something to the other. It's not magic. That's what I mean. Cool. So diffusion models basically just grab the idea that you just saw, can we train some sort of like codec that's noise robust? So the idea of diffusion models, it was proposed in 2020, so it's not so far away from us. So anyway, you have some real image, and what you want to do is that just add noise gradually. So, you can add some noise to it, so it becomes a noisy example of it, but, at the end, after usually 1,000 steps. So think about usually T is 1,000, that's the scale. So usually you gradually add the noise for 1,000 steps. So, at the beginning, it still look like the face, just with some tiny noise, but in the middle, it will become, less detectable, visible, but at the end, it just become pure noise. So what we want to do this is, the same, the noise in autoencoder, that codec that's robust to noise. So what we want to do is that this process is somehow sort of like diffusion process. So diffusion, the word comes from the physics and, statistics process, that you just, if you have, sort of like thermal transmission, that, you go from a very, very older cold hot stuff, and then it will just diffuse out. So the heat will, propagate out, and it becomes sort of like uniform. So that's the idea. So you add noise into your image. So that's what we call diffusion process. But what you want to do is actually doing denoising. So that's what we want to learn by the neural network. So what we want to do is to learn to get rid of the noise. So you can think about how they work is that, you turn this, slightly more noisy example into a slightly less noisy example. And you want to do this again and again. So how we do it is that you grab some image and you add noise to it, and then you turn it into a more noisy example. And now what you want to train is to go from this noisy example and go to a neural network to predict what the noise is, so that you can get a sense how you get the output less noisy version. Anyway, that's sort of the idea. So, in the training stage, what you want to do is add noise gradually to get all these examples. And at the generation stage, you just do the opposite. Just remove the noise gradually. That should be much easier in this case. So, when you're doing the generation, you get this input, just a bunch of, noise. And then you will just remove the noise gradually, going from the left to the right. So, that's what we were talking about, just that, in each step, you just remove a little bit of that noise and then apply it again and again for 1,000 step. Here we didn't show everything, but for 1,000 step, then you can get the output that has some structure. Question on this? Sure.
So is it randomly generated, or is this the noise that was generated from the forward diffusion process?
I think it's fine, but usually we just do random noise. Yeah. Because technically, once you do that, it should be no more distribution. Yeah. So usually during generation, we sort of like assume we don't have any ground truth. So, we just grab random noise. Yeah, cool.
So autocomputers trained on like different objects, or like why would these be going to different outputs for noise?
It's not trained on, it's like yeah, I think you're right in that, in each step, it's unknown whether how the model will translate that. It's like, going from this to this is not so obvious. You can go from this and turn it into an airplane, right? So it's, at every single step, there is some randomness that, the model can decide how to turn this, whether to turn this into a building or turn this into an airplane. It looked like an airplane to me, actually. But anyway, there is some randomness. So the model is trained to, model the whole distribution. So at any single point, it can decide, sort of like which direction to go from that. And it's a random process. So, if you do this again, maybe it will at some point diverge from this point and turn it into, like a, I don't know, look like an airplane, I don't know, or something else, I don't know. But you can definitely see that at the early stage is more coarse shapes, low frequency components. But at the later stage, it has more high frequency components. Yep.
So like a lot of the image generation things have prompts that you input.
Yeah, it will guide it. Yeah. Good question. So that's sort of like, relevant to your previous question that, there's all different, possibilities within each step. So, say we are at this stage, that how should we go from this toward the end? So, these text prompt, diffusion models, or, even image prompt, but whatever, some inputs to guide the model to do that is that, starting from this, if your prompt is, buildings, then it will just go toward that direction so that it becomes a building. But now if you go from this, but, you sort of prompt it with, airplane, then it will look into how to turn this thing, into more airplane-like shape. So that's sort of the idea of prompting that, within this 1,000 steps, because you are doing one tiny step at a time. So in each step, the model will just look at your prompt that, it's airplane, it's a dog, it's a cat, it's a whatever thing, but, sort of like guide your generation toward that goal. Yep.
that work?
How does that work? Neural network. So usually you have a transformer to turn that, input prompt into some embedding, but basically just a vector, but that vector contain all the information of your input. And that information will be put into this. So when you are doing this, now it's not just this image to go to this, neural network, but rather, there's another some text as input. So now the model is like, given the task, given this less noisy thing, how do you turn it into a slightly less noisy version of it that's closer to your target? And technically, it's just adding, an additional input there. There's another question. In training, there's still a ground truth in the sense that you use an image data set and analyze to train, correct? Yes. So yes and no. So yes, in the sense that you still have to have a data set, otherwise you cannot do anything. No on ground truth, I would say. So think about it. The clever thing about diffusion model is that, we do have ground truth, but that ground truth is, each single step in that 1,000 process. So, you can think about, why can't we just go from input to the output and just do it one shot? It just doesn't work because, the idea of diffusion is that you have the ground truth because you divide this process into so many different steps. So each single tiny step, there's a chance that you can sort of like guide the model's generation, and you can tweak it so that it follow the idea that follow the direction that you want the model to be. So that's sort of the key concept of it. So in terms of ground truths, I wouldn't say, you have ground truths as the output, but, for each single step, you do have some sort of ground truths, but that's, created artificially by adding noise. So you create each single pair of more noisy version and less noisy version, and, train this simple model that's only one of the 1,000 steps that you are doing. Cool. Questions? Good. Okay. We'll see. I mean, it's one thing looking at these models. It's another thing when you sort of like apply it into a certain domain. Cool. So now we can see how we can do this, diffusion models to generate music. Cool. So anyway, we talk about all the details, but sort of like forget most about it. What you need to know is that, diffusion sort of like, the first time I, learned about diffusion, this is the only thing I remember. Anything else, who cares? I mean, if I want to implement it, then I would look into it, but, sort of get a sense that, diffusion is doing this, tiny 1,000 step thing, and at each time. And what we want to do is try to remove the noise gradually. And it's some magic of a neural network. That's sort of the thing that we should keep in mind. So anyway, we can generate music using diffusion models. So nowadays people are doing audio generation directly, but now we will look into symbolic music first. So this is, 2023. People are looking into, can we use diffusion model to generate piano roll? So, at that time, is when we have seen all the cool, image diffusion model that you can do text to image generation. So in this case, they are just doing, this polyfusion, but basically generating polyphonic piano roll using diffusion. So anyway, we won't go into detail, but anyway, it can generate some nice music. Well, let me play some of it. Should we do? Let's look at this. Doesn't look right. Anyway, these are the unconditional generation, but somehow they don't have this nice, or maybe we do this melody generation given accompaniment. So we'll generate. And actually, so I guess if I click, it would. Oh, okay. So likely you've noticed that the data set is a C-pop, Chinese pop data set. So is more pop in the sense, and it's also a more, Lishi-like data set. So it's mostly just, right hand playing the melody and left hand playing the chords progression. But, it can be a arpeggio or, whatever way you play the chords. But that's sort of the idea, simple, composition. And, this is something that I want to talk about, cascaded diffusion models. So this is the first sort of like symbolic music generation model that can actually do full song generation. So before this, all these model, looking at, transformers, looking at GNs, none of these model can actually sort of like generate a full song with some structure. Usually, if you look at the transformer INN, it's just that, it can continuously just keep generating new stuff, but it's sort of like never actually ends, and it doesn't have, any long-term structure. And, GN diffusion model in earlier shape is like, it generates like fixed amount of, fixed lengths of music rather than some structure. So this is one of the first model that can actually generate music long enough and has some structure. So how does it did that do it? So diffusion model, what they want to do is that they use diffusion model in each single stage, in 4 stage. So in the first stage, what we want to generate is something like this. So at the top, this is the structure. So you have intro, and then A. So this is sort of like the chorus. So you have chorus 1, chorus 2, and then B is verse 1, verse 2, and then you have bridge, and then you go to chorus, verse again, and then bridge, and then verse again, and I don't know what X is, but likely verse again, but in the cooler way. And then finally you have outro. But basically you can generate this thing using diffusion model because it's just going from 1 to 0 for each section. And it's sort of like hint model. You can definitely use a diffusion model to generate this. And at the same time, it also generates something like this. This is the tonic. So you can sort of like figure out where the tonal center is in different section. And finally, this is the scale. So it's sort of like what chords, or not chords, but what is the scale of this sections. And so basically, cascaded diffusion model, the first stage, what they want to generate is something like this. And then you just turn this, using diffusion model, one step further in 4 steps until you get the final stuff. So, this is the second stage. What you want to go from this to a slightly more complicated composition. And so we can take a look on level 2, level 3, and level 4. So as you can see that, things get more complicated. So level 2 is still, you sort of like divide it. So the top would be the melody and the bottom would be the accompaniment. And these are simple melody. But at level 3, you will turn it into more complex melody. And at the end, they will be merged together. And it also has different time resolution. You go from beat to step so that, you get, much more complex temporal resolution. So this is a closer look. So in level 2, what we are generating is, a very coarse melody line. So this is what they call reduced melody. And in level 3, it will turn it into lead melody that's, more detail. So more temporal thing. And at level 4, we sort of like, down with the melody. So what we want to do is turn this accompaniment into the actual accompaniment that you are doing. So this is just chord progression, but now you want to go from simplified chord to, real chords, but at the end, turn it into accompaniment. Cool. We can listen to some of the example. But anyway, this is how they do it. An example of hierarchical wholesome. This is the intro. The verse. You will repeat again back to the chorus and verse again. So, it's basically repeating the same, motif and idea of similar melody from the first time it appeared. But anyway, you can look at how they actually generate the whole thing. So this is the first thing they generate. So, it's just the same tonic key, a piece in A flat. So, it's the same A flat over the time. And they generate this I4, A4, A4, B8, B4, A4, B8, O4. But basically, 4 measure of intro, this thing, and then 4 measure of A, 4 measure of A again, 8 measure of B, and then there will be a bridge of 4, and then A for 4, and then B8, and then finally outro 4. Anyway, and this is the second stage. So this is the first stage, and then the second stage is what they do. A simple chord without, all the arpeggios. And then simple reduced melody. So, you can get a sense. And now in the third stage, you generate the lead sheet. So now, the chord is still just pressing the chords without, any arpeggio, but now you finalize the melody. And finally, you get everything. So, the last step, you only generate the accompaniment because now the melody is done. You turn this thing into the actual, left hand. Cool. So that's how they do it. It's sort of a very cool way to do it, because before this, it's sort of like kind of totally impossible for us to imagine how we can do, sort of like some structured generation. But there's still a lot to be done. This is very simplified version of the music that we are aiming for. It's a specific genre and also specific type of arrangement. It doesn't generalize to other type of arrangement, but it does shows that if you have this kind of data, you can somehow train something on this to sort of like imagine that whole song generation goal. Questions? No questions? Okay, cool. Anyway, we will look into some of the other diffusion models being applied to audio, and at the end, looking at some of the state-of-the-art music generation model nowadays. This is state-of-the-art in symbolic music, anyway. Cool. So in the last few slides, I will just talk about some of the other models that just not just doing just generate music, but rather in a more iterative way. So these models we call it music and feeling models. But basically what we want to do is to sort of like fill in the gaps. So this one model is called debug. So it's sort of using this very cool representation where how it does it is you have an A4 and then you just hold that note, so you just for underscore here, and it also have this counter on the beat, so 1 2 3 4 1 2 3 4 1 2 3 4 1. Anyway, that's how they do it, and they also encode the fermata here. So everything else is 0, but you have a fermata here, so you have 1 here. But anyway, what it does is using this, I don't know, always feel like this look like a face. But anyway, what it wants to do is that given somehow I don't have any annotation. So the blue one are the past information, and the gray blue one is the future information, and you also have the current other stuff. So basically use all of them to sort of like guess what this green one is. So debug is sort of like using this algorithm that, this is the whole algorithm of it. But anyway, the idea is that, at each single time, you just grab one of the position, grab one of these, and then mask it out and use all the other context information to predict what it is. Anyway, this is what we can do with debug, reharmonization. So the soprano line is given, and it generates all the other. Cool. So this is back in 2017. But anyway, this is the main model that I wanted to talk about. This is called CocoNet. It pretty much have this sort of like similar idea, but now we are doing this in feeling model, where the model is like looking at this piece, we mark out part of that and try to recover it. But at the same time, you can also get rid of all the other things. So now this sort of like become a harmonization model, but you can also just mark out everything and have the model to generate everything from scratch. So that's sort of the idea how CocoNet work. We won't go into detail, but the idea is that you apply this random mask to your input music, and what you want to do is that to recover all those missing parts. So this is what you can do with such a model that, at the beginning is just, purely chaotic, random generation. But at each single step, you just, look at those, you fix those are more confident and you treat those as, done deal. And then you look at all other, less confident nodes and try to figure out which would be the better notes for those. There's no sound. Anyway, yeah, there shouldn't be any sound anyway. So this is the process, how CocoaNet work. So let's look at it. So initially, the blue nodes are given. So it will generate these things. So it's a heat map. Some of them are very certain that the model think that, well, we should just do this here. We should do this base node here. We should do these, the same sort of like 3 degree below thing. But some of the other nodes, the model is not so sure about it. So, later in the stage, it would sort of like keep these, more confident nodes. But at the same time, look at all the other less certain nodes, try to improve those. So, and, as time goes by, at the middle part, that now most of the nodes, you sort of have an idea that, those are the nodes, but there are some of the details that you are not quite sure yet. And then you keep sort of like rearrange some of the details, and until the end, you sort of like converge into what you want. So this is sort of like how CocoaNet work internally, how you do this optimization. Cool. So this is some of the music it can generate. Oh, this is, I didn't notice that. Anyway, this is what you can generate. Cool. And this is actually behind the bug doodle. So if you ever play it, it's pretty cool. So have fun. So, it was out. Cool. So basically you can do, I don't know, this. How can I drop that? uh, cool. That's just basically running CocoaNet under the hood. So once you give the the subfile online, you can also use another one. You like it? Anyway, you can play with it online. There's also some blog you can look into. Any question on this? Cool. We don't have time for these, but we will cover it likely fast forward over these, and we will look into the audio thing next next week. Cool. So that's it. So on Wednesday, please be prepared to talk about your work. What you want to work on, these things. It's on the slides. and don't be too panic. The goal is to have you be prepared and progress on your project rather than being, terrified or, being harsh. Cool.